Hey, here we are again. Now we're in section 7.3, which is a different way of integrating or using integrals to figure out the volume of revolution. So let's read this problem. It says, use cylindrical shells to calculate the volume generated when the region bounded by y equals, hey, it's our friend, y equals the square root of x, and y equals 1/2 x is rotated about, this time it's rotated about the y-axis. Okay, so typically what we do is we draw this. I'm just saying it's familiar because it was in the last video. We know it goes from 0 and that this point is 4, 2 from the previous experience. Okay, so here's the thing. If you slice and dice as we did before, like this, and when you do that, you got this little rectangle, whatever you want to call it, whatever it might be. Okay. When it rotates, it's not going about the x-axis. It's not fanning around and creating a washer. You're not looking at an area anymore. But instead, what it's told to do is let's go around the y-axis now. Okay. So as we go around the y-axis, well, it creates this kind of shape, right? That's like a cross section this way, but it's not. We're not slicing it perpendicular to the axis of rotation like we did in the previous video. Instead, we're slicing it actually parallel to the axis of rotation, so that if I take that rectangle, it spins, this little, like pretend this is an area, but what happens is it spins around the y-axis like this, and if you go really fast, it creates a cylinder, okay? A cylinder. So the cylinder I'm talking about is looking like this. I always have trouble. You know how wonderfully artistic I am. Like that, something like that. So it creates this shell. And the thing about it is, then you do another, and you do another, and you do another, and do another, and they're all creating these nested shells, kind of like Shrek and the ogre, and he has layers. These are layers of your volume that we're going to unfurl them and try to calculate their volume. And that's the method of cylindrical shells. You have this guy, but inside this guy, you have another guy nested inside. And it could be the curve is doing whatever it's doing, but you know, and they just keep nesting and nesting and nesting inside each other. And so that it's a clever idea, I'm telling you. And when someone comes along with a knife and like cuts one open like this and unfurls it, right? Like this. I mean, there's a thickness to it. We sliced it open like it's a, you know what I also think of is that fruit roll up, you know, you just cut it and it unravels. It's a solid, but the unravel and it's really thin. But anyway, this is what we're looking at is it's approximately a rectangular solid. Okay, and that's how we treat it, because what we would say is, say I'm going to look at this guy right there, and this is like the ith subinterval. And then of course, if I can do it for one, I do it for all of them and I add them all up, and I just want the volume of this thing. Well, a rectangular solid, the volume is length times width times height. Now listen, we have some of this already. There is a thickness to it here, and that thickness corresponds to this thickness, and guess what? It corresponds to that thickness too. And that guy is delta x. So the thickness is delta x. There's a height to it. There's this height here, right here, that corresponds to this height, which corresponds to, oh, this height right there from here to here. Well, in terms of x, it's the top curve minus the bottom curve. And so for us, that is equal to radical x minus 1/2 x like so. Okay, that's enough right there to boggle you. It's like, okay, delta x, and that's that. But then the last part is this part. How long is that part right there in our problem? That's the best part, the funnest part about it, because it's a shell, it goes around. What happens is you're talking about choosing x and try to figure out how far around he goes. You know what that is if you look at it on face value? It's a big old circle, isn't it? And if you start here and you run around this circle and you stop here, you just did the whole circumference, and the whole circumference is 2 pi r. So for us in our problem, I better choose another color here. For our problem, we need to know what that r is. Cool. So we're going to say that whole thing is really 2 pi r, and r corresponds to this distance, and that distance in this picture is here. How far is the rectangle from the axis of rotation? And you just pick an arbitrary x there. See, we're going to go out. X is how far this is. Top curve minus bottom curve, plugging x in, that tells you the height. The x going out is actually a radius. Okay, so maybe not okay, but I'm going to say this anyway. I'm going to say the volume sub I of the ith subinterval that's spun out like this. What's the volume? Well, you can think of it this way. It's the area of the rectangle, which is delta x times radical x minus 1/2 x, and then how far does it travel? And it travels 2 pi x. So the volume is approximately equal to, let's say, 2 pi x sub I, and then, let me clean that up a little. Math always gets me excited. So we have, and then we have radical x sub I minus 1/2 x sub I. If you're following me, that is. So for us, the volume is approximately, let's see, let's add them all up. I equals 1 to n, and then you go 2 pi x sub I, and then radical x sub I minus 1/2 x sub I. Now, you don't have to do your homework this way. There are formulas to use, but as we take the lim, provided it exists, as n goes to infinity, here comes our integral. We're going to integrate. We're slicing and dicing, remember, in this picture, from 0 to 4. There's a 2 pi. X stands for that. And then we have radical x minus 1/2 x, and then dx. I forgot this guy at the end. There's a delta x. Oops, sorry. The delta x turns into the dx. And this is where we're at. This guy's set up correctly. So you want to go back and look at it. And you can pause and you rewind and go, what the heck did he do? But I do want to fill this in. When you do the this is the shells method, okay? And when you do it, I like to think of this is the radius, and this is the height. And if you need to think of it, this guy, that's the thickness of each cylindrical shell, okay? The radius, though, typically is, to be more general, it's, you know, because you're going to want to say it's always x, and it's not always x. What it is it's how far from the axis of rotation, I'll say, the rectangle is. That's how I think of it. And the height is how tall is the rectangle. And so when I ask those questions, you got to first of all think, oh, I'm integrating with respect to x. So when I do this, everything has to be in terms of x. And that's what we have here. So really quickly then, to finish this off, if you want to watch, that's fine. But maybe the setup is the most important thing. But those of you that want to watch, what we'll do is I'm going to factor out the 2 pi, integral 0 to 4. I'm going to distribute here and get x to the 3/2 power minus 1/2 x squared dx. Okay, let's integrate. Don't forget the 2 pi. And we've got, this guy is x to the 5/2 over 5/2, which means 2/5 if you invert and multiply x to the 5/2 power. You can work that one out. And then minus, looks like we're going to get 1/6 x cubed from 0 to 4. So the 0 is not going to contribute anything, you know. So it's really just the 4. So we have 2 pi. And in here we plug in the 4. Oh my goodness, the square root of 4 is 2, 32, 64/5. You can verify that. And minus, you plug in the 4, that's 64/6. That's interesting. And I'm going to factor out the 64 and say 128 pi. And really you're looking at 1/5 minus 1/6. So really over 30ths, is that right? 6/30ths minus 5/30ths. This is old school. I know you guys don't know what I'm talking about. Just kidding. 128 pi. And then times 1/30th, which I think reduces down to, I think, 64 pi over 15 is the actual exact volume that we generated. This is a longish video, so I'm going to stop it, but there's a lot of information there to look at, and that's cylindrical shells. All right, we'll see you at the next one. Okay, guys, study, study, study.